Hiya! So in this video, we're going to look at area and determinant. In particular, we're going to focus our attention to a two-dimensional space. So here, what we're going to do is we're going to let A and B be two linearly independent vectors. In other words, they're not collinear. So in other words, the vector product is going to give us something that's not zero. And we're going to have them live in two-dimensional space. Now, if you kind of remember the vector product, we defined everything using 3 dimensions. So how do we go from 3 dimensions down to 2? Well, this is not too hard because we can think of 2 dimensions as being a plane in 3 dimensions. So like we have 3 dimensions, right? We can consider a plane, so like some flat surface in this 3-dimensional space. So that gives us a plane. And our aim is to calculate the area of the parallelogram on this plane. So what we're going to do is we look at our vectors a and b, right? So we have some like 2 vectors a and b. And these 2 vectors, there's going to be some plane that contains these 2 vectors. So we're going to kind of look at the area in this plane. So what we're going to do is, so since we have this plane, we're going to let n be a unit vector in E3, which is orthogonal to this E2. So in other words, we just look at this, we take some n, and this is going to be orthogonal. It doesn't really matter which one. If we change sides, then we just have to replace alpha with minus alpha. It's not too big of a deal. But what this basically says is because that these alpha cross beta, right, since this is in the space as n, right, what this means is alpha cross beta is just alpha times n for some alpha. And in particular, alpha is going to be the area of the parallelogram formed by A and B. Why? Because remember how we said that the cross product is going to be precisely the vector orthogonal whose length is the area. And since n has unit vector, in other words 1, the length is 1, so you multiply the lengths. That gives you the length of the area. So alpha is really just the length of the area. So let's kind of do this. So we let E and F be an orthonormal basis. So it doesn't matter what, choose your favorite orthonormal basis in E2. And again, remember that we chose this in some direction. So EF, and then we're going to add N. So we're going to, since we have some order, we're going to EFN is going to have the same orientation as E3. Now this is equivalent to just choosing E and F to have the same orientation as A and B. So in other words, we're just choosing E and F and AB to have the same orientation. So this is important. If we had different orientation, remember we would have to take minus n and things get a little more weird. So it's just easier to say it's in the same orientation. So here, what we have is, since we have E and F is our basis, we can write A and B in terms in E and F. And then if you kind of notice, there's nothing in the third space. So here, the cross product is just equal to this determinant, but the third entry in each row is equal to 0 because there's no n component when we write these as a linear combination, because A and B live in this hyperplane, in this plane. So in other words, what we're basically saying is that the nth component is always 0. So in other words, we can just look at n and the submatrix here, and that gives us the cross product for A times B when it's living in 2 dimensions. Now n, do you remember what n is? N is just our unit vector. So in other words, the area, this here is just the area. This is our area. And then here we're kind of discussing like, oh, if we had chosen the opposite vector, right? Like things would kind of be opposite and it'd be weird. And so what we're just going to do is, instead of worrying about, oh, did we choose the right vector? We chose the wrong vector. We know area is always positive, and all this is going to change is this sign. So since it's only going to change sign, what we're just going to see is that the area is going to always just be, so we can kind of always consider this as our area. So it's just the absolute value of this determinant. Yeah. So what we're gonna now do is, so we see in 2 dimension that the determinant is really giving us the area. So before we, there's only one proposition, so I'm just gonna finish it up. So before we finish, we're gonna talk about a linear operator on the parallelogram. And it turns out that this linear operator is determined by our cross product. So if we let P be a linear operator, A and B be two vectors, and we're gonna denote A prime to be P of A and B prime to be P of A, then what's the area of, so if I have these two vectors and I look at the linear operator, I do a linear operator transformation on these, what's the new area? This is like the question we're asking. And it turns out that it's almost the same. I almost gave this away. So it's almost the same. So we have the area here of the parallelogram from the original one. But in front, we want to keep track of how much our linear operator is distorting our area. And so this is what the determinant is basically doing. It's saying, or what the determinant here is doing, it's saying that you want to keep track of how much this distortion is happening. So a quick little proof, basically what we have is that we start off with some basis. Oops, wrong color. This font. Nope, where did it go? Some basis, and then we let A1, so we write everything out in terms of this basis. Then we look at the coefficients of A prime and B prime by multiplying the matrix by each of the column vectors, blah, blah, blah. What basically is happening is we add the coefficients, right? Because we've now done the linear operator. So after acting on the linear operator, acting with P, right? Since P of A is equal to A prime, so what this gives us is precisely like stuff like this. So like P of A1, E1, for example, is going to be P1, 1, A1, E1. This is basically what we're saying here. And so we're left with, so this is what we saw before, what we kind of showed. We have this equality. Now here, you'll have to notice that these two matrices, you can separate this into a matrix times the matrix. And since the matrix times the matrix, you can always split up. Since you're looking at determinants, you can take determinant of one, determinant of the other. And since it's just multiplication, you can move them side to side. It doesn't really matter. This is just the transpose. So that gives us P of T. And the determinant of P doesn't change if we're looking at the transpose or not. And this is just the original area. So I went over this quick, mainly just to see what it is. You don't have to like memorize this or anything. But yeah, so basically, if we have a linear operator, we have an area, we just multiply the determinant with the area and we get our new area in the new space. So it's kind of nice, cool little thing to see. So we'll stop here because next time we're going to look at the volume. So what happens with volume in 3 dimensions rather than just looking at how we had like these two kind of perpendicular things and we want to figure out area, how do we do volumes? And in 3 dimensions, this is related to determinants in the same way as area was in 2 dimensions. So I will see you then.